All right. This example, we are going to discuss the fault calculation when the generators are loaded. Once the examples that we have discussed earlier in the class is that the generator was, if you remember correctly, right, the generator was not loaded. Okay, and then we just introduce the fault at the terminal of the generator. Okay, that was, of course, this is very serious problem. This is one of the worst, right, scenario that would happen in the systems. And it's rarely happen in reality, right? But this is the case that you may see in real life, right? The uh, generators are loaded, and then there is a three-phase fault just happened at the load of the system, which is the machine of or the motor, right, on the other side. We can discuss this in detail, right? So this example is from Granger Stevenson book on from example 10.1, right? The problem says that the machine, right, the two machines, generators and the motors are identical, right? Synchronous generator and motor are rated at 30 MVA, 13 kV, and both have subtraction reactances. Okay, these are subtraction reactances of 20%. Okay, given this this kind of statement, that this is given in terms of per unit, right, based on the rating of the machine, right? So this 20% means that this is the 20%, right, of this bases, right? So you can see that when we give the base, right, S base or a power base and kV base, right? So given these two, right, you would be able to see to find the impedance base, right? 20% means that this is just 20% of that set base, okay? But this kind of problem, right, we will do everything in per unit calculation. Okay, the line connected between the generator and motor have reactance of 10% based on the machine ratings. Okay, based on the machine ratings means that based on this the same base, right? 30 MVA, 13 kV. The motor is drawing 20 megawatt at 0.8 power lagging at voltage terminal of 12.8 kV, right? Once I mean, when the motor is loaded, right, at this condition, right, a symmetrical three-phase fault occurs at the motor terminal. Okay, so the problem just asks you to determine the fault current, okay, fault current or the short circuit current, right, of this symmetrical three-phase fault. How much the current is it, right? And the problem also asks you for the contribution or the subtraction current, right, from the generator, right? Subtraction from the generator, subtraction fault current from the generator and from motor. Okay, to be more specific to this problem, right? I just to rewrite the problem a little bit, right? If you read find the subtraction currents in the generator, it's not really meaningful. Okay, you may be confused, right? I would need to change this statement a little bit. So I ask you the contribution, right? So the problem just asks you the contribution of the fault current from the generator or contribution of the fault current from the generator. Okay, and also the second question asks you the contribution of the fault current from the motor, right? The fault contribution of the fault current from the motor. Okay, now the third question asks the total fault current. Okay, if you interpret the question in this way, you can see that the question, right, the problem, the question number three, just the sum of the question number one and two, right? If you manage to know the contribution of fault current from the generator, right, you know the number two, the fault contribution of fault current from the motor, right? The total fault current would be the sum of the two contributions, right? And the key concept of this is that by using the internal voltages of the machine. So this is the key that that's why I highlight this in red, right? Why is it the highlight of the calculation? Let me draw this picture again. So may I draw this on this page so that you can map the statement to the diagram that I'm drawing now. Okay, so you can see that this is the generator. This is a gen, right? The generator, we model this as the voltage source behind the reactance. So the reactance of this is the subtransient reactance of 20%, which is zero point 0.2 per unit. So I write this in J because we will use this later for calculation, right? So this is the internal electromotive force of the gen, right? And this is the terminal of the generator, right? Then the problem says that this generator is connected to the motor. So the motor is also use the same model, right, which is the voltage source behind the reactance, and of course with the same rating. So it's identical on both sides. So the source, which is on the left, and the load on the right, is connected through the transmission line with reactance of 10%, which is zero point 0.1 per unit, right, based on the ratings of the two machines, right? So this is clear that this is on the right side. This is the terminal. I'm sorry. This is the EMF internal, EMF of the motor, right? Of motor, and this point is the motor terminal. Okay, and the problem asks, that we want to calculate the fault current, right? When there is a fault at the terminal here, a fault to the ground over here. So the problem number three asks you what is the short circuit or the fault current flowing from this bus to the ground, right? So you can see due to since we have the generator and the motor, so this fault itself, the fault current itself, is the contribution of the fault, right, that is made by the generator, and the contribution of this fault current from the motor, right? So we need to work on this. Okay, you can see that the fault current is the fault that is that is flown from the generator, right? And the fault that is contributed by the motor, right? And we want to analyze the system during the subtraction period. Subtraction period, we have discussed it earlier, right? That the subtraction period is the short, very short period right after the occurrence of the fault. Okay, subtraction period is the at the very first instance, right, after the inception of the fault, right, just right after the fault. So this is subtraction is just, the key is that it's just right after the fault. When it is right after the fault, right, you can see that we have discussed it already, that just right after the fault, the machine itself, right, it's an it's energy storage element. If you model the generator, right, it's a kind of, it's a kind of energy storage. I'm sorry, it's not energy storage, but you model this as inductance, right? So you know that the flux, right? You have discussed it already. The flux in, right, cannot be changed instantaneously. This is the concept. The flux of the machine cannot be changed instantaneously. That means that before the fault and right after the fault, right before and right after the fault, right? The flux cannot be changed instantaneously, right? That means that the internal EMF, the internal EMF, it is the force that is developed by the machine, right? The EMF, right, remain, right, unchanged after, right after the fault. Okay, so the internal EMF remains unchanged, right after the fault. That's why this problem just suggests you that you have to calculate. You should calculate the fault current by using the internal voltages of the machine. So this is the fact that the example here used. This is the underlying assumption, right? So the internal EMF, internal voltages of the machine can be analyzed or can be calculated, have to be calculated before the fault. Okay, before the fault. So before the fault, the problem also states the uh, operating condition before the fault. Okay, you should highlight this one. Okay, the model is drawing this power at this given power factor at this voltage level, right? This is the condition right before the fault. Okay, this condition is the condition before the fault. Okay, so this blue highlighted condition, right? You would be able to what I have reiterated this several times that if the problem gives you power factor and the voltage, you can find the current, right? Straight away you have to find current. So soon after you find the current, you look at the equivalent circuit, and then you can find the internal EMF of the both machines, both generator and the motor, right? So you have to analyze the circuit right before that, and you just use this condition that the internal EMF cannot be changed instantaneously. So during the subtraction period, right, the internal EMF remains unchanged. You use the same to calculate the fault current, which I will show you just now, right? So you can see from this circuit, right? I will have to draw this picture first before I will dive into the calculation, right? So this is the generator G and the internal EMF of 0.2, J 0.2. Then we have 0.1, which is transmission line. This is the terminal of the motor. This is the internal reactance of the motor. This is motor. Okay. Okay. And this is E, right? EG, and this is EM, right? If I analyze during the fault, right, during the subtraction period after the fault, at motor terminal, at the motor terminal, which is here, right? So right after the fault at the motor terminal means that it is in the subtraction period, right? It is during transient, right? This is the fault current, right? So the problem asks you, the problem number 3 asks you to compute this IF double prime. So you can see that, this IF double prime is the contribution of the fault current, right? Because you can see that we have two sources, right? So you can use the superposition theorem, right? You use the superposition theorem. So you could see that, this IF double prime is essentially the contribution from the generator, and the sum of the contribution from the generator plus the contribution from the motor. Of course, this is during the subtraction, so we put the double prime over, right, as the uppercase, right? And superposition here, you can see AF. I highlight this in as a complex, right? This is IFG double prime plus IFM double prime, right? Now, due to this superposition, so you can see that you have to split this, circuit into two, right? The contribution due to the generator, can be determined when the contribution or the source and the motors is deactivated, right? So at this point, right, it can be it can be computed from this equivalent circuit, right? J.2, J, sorry, it should be here, J.1, okay, J.2, and this part, the motor is deactivated. The activation of the voltage source is by, short circuit, right? The voltage is the same, and the short circuit is over here. So this is the IFG double prime, right? And okay, this is what we are going to do, right? And this is EG double prime, okay, EG double prime. I put, the underscore because this is complex quantity, right? So in this particular, in this equivalent circuit, you can find the IFG double prime by EG double prime divided by, because the current flows through these two reactances. So this is J.3. This is the first, right, part of the fault current coming from the generator. Okay. So the second part here, okay, would come from this circuit, right? This is the circuit from the motor side, and the generator side is deactivated, and there is a short circuit over here, right? This is EM double prime, the potential over here, and this is J.2, and this is the current, right? The current flow in this loop is the IF, the fault current coming from the contribution of the motor, right? Now you can see that the fault current through coming from the motor, right? IFM double prime is the EM double prime divided by J.2, right? Is it okay? Now you can find, if you manage to find this EG double prime, you can answer the question number 1, right? This is number 1, okay? You have to be able to find EG double prime, and to answer number 2, you need EM double prime, okay? And then how do we achieve, EG double prime and EM double prime? You rely on this statement, right? That the internal EMF remains unchanged right after the fault or during the subtraction period, right? So, given this fact, that the EG cannot be changed instantaneously after the fault, right? your EG double prime or the internal EMF during the subtraction period is the same as the internal EMF before the fault, right? This is before the fault, okay? And similarly, the EM double prime can be analyzed in the same fashion because, it is essentially EM, it is equal to EM before the fault, okay? So now, you have to analyze the circuit right before the fault. Okay, you have to analyze the circuit before the fault. Once you know the EG and EM before the fault, you could find the EG double prime, which is the same as the EG, right? You can put the EG and EM that you find from the circuit before the fault. Okay, that's what you have to analyze, right? This is the before the fault. How the circuit would look like when before the fault, it's still the same circuit, right? But the given condition are, given, right? This is the VT, right? VT of the motor, okay? Terminal voltage of the motor. And the problem gives you that when during the normal operation, VT here is 12.8 kV, right? And it is drawing, right? It's taking the power from the source. This is G and this is M. It's taking power at 20 megawatt and 0.8 PF lagging. All right, the 0.8 PF lagging, the voltage at this much. So what you would do is that P, V, power factor, so you could find the line current, which is 20 megawatt divided by root 3 times V line, right? 12.8 kV times power factor, which is 0.8, right? It comes from this formula, P of the three phase, which is root 3 times V line, I line, cosine theta, right? This is the formula. So this is, right, you can change this to IL. If you put this in terms of, this is just the magnitude you can see from this formula, right? There is no complex quantity in this case. But if you want to write in the phasor, so you have to put the angle. So you can see that this is lagging power factor. If you lagging power factor means you put V as a reference and I, right, as a lagging power factor. So you see that the I is essentially negative. So it is negative of R cosine 0.8. This is solution of this, once you calculate this number, you get the unit of kiloamps, right? This is in kiloamp. If you want to change this to per unit, right? Why do we need per unit? Because you need to compute the EM right here and EG right here, right? You need to compute this. So when you do the calculation, don't forget your goal, right? You need to find this EM and EG, right? EM, EG. This is EM. You need to find these two, right? In order to find these two, you have to work in per unit because this is J.2 per unit, right? J.1 per unit, and this is J.2 per unit. So you have to work everything in per unit, right? So you need to change this IL to be in per unit. So remember, you have to convert this to per unit. So you need your I base. The I base, the common base, as this problem states, is that the reactances are based on the rating of the motor, right? The rating of the machines, right? The rating of the machine is what, 30 right? The problem says this is 30 MVA, so both of them have the same rating, 13, 13.2 kV, right, as a kV base. So the I base essentially, right, 30 MVA divided by root 3 times 13.2 kV, right? So you can change this, IB. Remember, the IB here is in real quantity. There, there is no base in complex quantity, right? Remember this fact, right? So you can change this IL in real quantity to be per unit, right? You take this divided by this, right? I'll just draw, a rough calculation, and I have computed everything, right, in the slides, and you can recheck this yourself, right? I will just put 20 divided by 30, right? These two, right? And root 3 just cancel. You become 13.2 divided by 12.8 and divide again by 0.8. So you get this 0.8594. The angle, right? This is arc cosine of 0.8 is 36, right? 0.87 degree. And this is in PU, right? Uh, this is in PU. Okay. Once you know this IL in per unit, you can see that the same IL flows throughout the entire systems. What what I mean? We compute IL, so there is no transformer, so the IL is the same, right? Even there is a transformer, the per unit quantities remains unchanged, right? You learn it from power system 1, right? But if you talk about the real quantities, if there is a transformer, of course, the current levels in each of the voltage zones would be different. Okay, but the per unit quantities remains the same, right? But in this case, since there is no transformer, so the line currents in generator on the line or at the motor remains the same, right? Now you can see that the IL is here. You know the VT at this position, right? What do we need to see is that we want to find the EG, right? The EG here and the EM over here. So you can tell straight away that the EG itself, you know, uh, it's here. The current flow from EG to the VT. So the EG just got the higher potential, right? Higher potential, that would be, the voltage at the motor terminal. Of course, this must be in per unit, right? So it is 12.8 kV, right, divided by 13.2 kV. These are in kV, right? This is to change in per unit, right? Since the angles are unknown, right? No, this is not angle are known because this is the reference, right? At the motor terminal, right? So the angle reference angle is 0 at the motor terminal, right? So you put the angle of 0, right? This is the VT. Now this is becomes in per unit. Uh, this quantity is VTM. Okay, terminal voltage at the motor in per unit. Of course, EG must be higher, so you have to plus the voltage drop across these two reactances, so they have J.3 times the current IL, right? So this is the EG, okay? So your EG here would be, 1.1432 and the angle of 10.39, okay, PU. And your EM is given by the EM, of course the voltage is less than the VT, so it is your VTM, okay, minus J.2 times IL, okay, and this you would get 0.877 8.774 and the angle of minus 9.02 pu, right? Now you have got this EG and EM, right? You use this fact, right, that the EG before and after the fault during the subtraction period are the same. So this is, EG during the subtraction, and this is EM during the subtraction. Okay, knowing these two, right? Knowing these two, you can put this value back to this equation number 1 and equation number 2. You can find IFG and IFM during the subtraction period, right? Okay, which is here. If you, I have put all the calculations for your reference. You can go through this again. So you will put the value over here, right? This is the EG double prime divided by the the sum of all reactances, right? Reactants that associated with the this picture, right? This picture, okay. And this is the IG double prime, IM double prime. So the sum of this, just be negative J 8.081 per unit, right? You just multiply this by the base quantity, right? The I base quantity. The I base is, I think we have computed somewhere. This is your I base, right? Which is here. The value is 1.3122 kiloamps, right? 1.3122 kiloamps, right? So you can see that the fault current is minus J 10.6 kiloampere, right? This is how we can use the circuit theory to determine the fault current, right? Of course, we will develop another method to solve, which is hopefully easier than this method. This is called Thevenin's method, right? In this case, we use superposition. The other case, we will use Thevenin. So the next video clip, I will explain to you how to solve this example again by using the Thevenin's method, right? Okay, see you next clip.